Welcome back to the second video on combinational subsystems. You might be wondering why the video is titled Combinational Subsystems 1A. In the previous video, we discussed a few basic combinational building blocks like the multiplexer and the decoder. We also identified a couple of important coding practices that have to be followed while modeling combinational subsystems. Of course, initially I thought of introducing you to modeling of more combinational building blocks, but we will take a slight detour in order to get introduced to some very important concepts related to timing and synthesis. So the topics that we will be covering will be of an introductory nature, of a very introductory nature, where we will have a short glimpse of timing and synthesis. So a peek into timing and synthesis. So the agenda is as follows. First, we will look at delays in the context of combinational circuits. Next will be a brief introduction to hazards and glitches. And finally, we will briefly look at the synthesis aspect of a particular fragment of code. Now, why this detour? Even though we know that behavioral modeling significantly reduces the design effort of digital subsystems, it is always important to know how your model will eventually synthesize into a digital hardware. The nature of the underlying hardware and its behavior, especially in terms of timing, should be clearly understood in order to avoid a lot of problems that are likely to crop up post synthesis. So that is the reason why I am introducing at least some basic ideas related to synthesis and timing at this early stage. Of course, this is by no means a full-fledged study of timing or synthesis, because that is such a vast domain. Of course, we will be exploring timing in greater detail when we discuss sequential circuits, because unless you know the structure of sequential circuits, uh, the nature of timing issues cannot be understood at a global level. But at least for the time being, it is important that we know how the hardware that we are modeling will translate or will synthesize, and also what will be the uh, different issues associated with timing. So in this video, first we will briefly look at the cause of delays in combinational circuits. Then we will examine a very important aspect of combinational circuit synthesis, that is the presence of hazards which lead to noisy behavior. Hazards lead to introduction of internal noise in a system. Even without the presence of external noise sources like EMI, we can have noise being introduced internally, and the primary reasons are hazards. So we will briefly look at hazards and how they lead to uh, glitchy behavior in combinational circuits. And of course, we will briefly look at synthesis in the context of combinational circuits. So that will be the agenda for this lecture. Now we will start with delays in combinational circuits. Delays in digital circuits are caused by the switching of RC elements. Caused by switching of voltages in RC circuits. The R and C being offered by the resistance and capacitance, not only of the MOS transistors, but the interconnects also. So R and C are due to the MOS as well as the interconnects. Now for illustrating this, we can take up the case of a simple CMOS inverter where you have a PMOS transistor that pulls up the circuit to VDD and an NMOS transistor pulling it down to ground. So let us see what happens when the input, say, switches from 0 to 1. When the input is 0, the NMOS transistor is open circuited and the PMOS transistor is conducting, thereby pulling the output to VDD. This is what happens. Now, when you are switching the input from 0 to 1, there is a transition. There is a transition during which the PMOS eventually goes to off condition and the NMOS becomes on. So this transition or this switching can be roughly modeled as the discharge of a capacitor. The capacitor initially is charged to VDD and it discharges through the NMOS transistor. So we are replacing the NMOS transistor by its equivalent resistance. So essentially you can see that what happens is a discharge of a capacitor. So if you observe the output, it will exhibit the characteristics of a capacitive discharge, which means that you will have a waveform which is something like this. And the total time that it takes for the capacitor to discharge will be the delay to switch from logic 1 to logic 0. This is the switching delay. Similarly, when the input is switching from 1 to 0, the reverse takes place. That means the circuit basically charges. It charges to VDD. So you have a capacitive charging where the RC path is offered by the resistance of the PMOS transistor and the capacitance of the output. The capacitance will be the sum total of the capacitances seen at the output. Let us not go into the details of how the capacitance is modeled. Nevertheless, for the time being, it is sufficient to just understand that the capacitance at the output is the sum total of the capacitances seen at the output. So the switching of the output from 0 to 1 and 1 to 0 does not take place immediately. There is a delay between the transition from 1 to 0 or 0 to 1 at the input and the instant at which the transition is seen at the output. So this is what we describe as the propagation delay. So essentially the delay is due to the switching of the RC elements in the circuit. And these elements need not be from the capacitances and resistances seen in the MOS transistors. They can also be seen in the interconnects. So basically what we are modeling as C here or R here will be a lump value which consists of the capacitances as well as the resistances due to the transistors and the interconnects. Of course, modeling this capacitance or these capacitances or resistances is out of the scope of our discussion, but sufficient to understand that the propagation delay that we are talking about is due to the switching of the RC elements in the circuit when the input switches either from 0 to 1 or 1 to 0. Now, when we are simulating the circuit using a digital simulator like Model Sim or the Vivado simulator or any other simulator, we will be seeing only the logical depiction of the input and output waveforms. That means what you will be seeing here in a digital simulator will be just the logical transitions. So if you are not accounting for the delays, then the transitions will be shown immediately. That is, if you are not incorporating the timing in the simulation, say for example, if you are doing behavioral simulation, the transitions will be seen immediately. But if you are also incorporating the timing, then the transitions will be shown after a delay, which is equal to the propagation delay of the circuit. So what you have to notice here is that the digital simulators, which are concerned only with simulating the circuit logically, they are not concerned with the shape of the waveform. Please remember that the digital simulators are not concerned with the wave shape. They are only concerned about the logical behavior of the circuit, and if timing simulation is carried out, then the lumped delay of the particular circuit will be reflected in the output. It will be shown as a total delay after which the expected transition is shown. So this is the case of the digital simulator. Basically, the digital simulator compute the output based on the logical relationships between the input and the output. They are not concerned with the wave shape. That means you cannot see the capacitive charging or discharging effects when you are simulating these circuits using the digital simulators, because their purpose is primarily to verify the logical functionality of the circuit, the functional correctness of the circuit, and also the behavior of the circuit when you include timing information. But if you are interested in observing the switching behavior of the circuit in greater detail, like if you want to see the waveform in its real shape and the finer details of the transitions, then you have to go for a spice simulation. In digital simulators, we will be able to see only the functional behavior of the circuit along with the timing, where the timing is where the timing will be shown just as a delay between the input and output. In fact, the digital simulators, they extract the timing information from the libraries. When you are synthesizing an HDL model to a target platform like an FPGA or an ASIC library, the timing information is provided by the vendor, the vendor of the ASIC library. And the timing information is usually provided in a format called the standard delay format. So when you are performing the timing simulation of a circuit using a digital simulator, the timing information of each and every gate in the circuit is extracted from the library, basically from the standard, basically from the timing information specified in the SD format. And this information will be used for incorporating the timing information in the simulation. So this is how delays are handled by digital simulators. Now let us see how this delay will manifest when we synthesize a piece of HDL code targeted at a hardware platform like an FPGA or an ASIC. To illustrate this, I am using the Vivado tool. So this is by no means a tutorial on synthesis. I am using this flow just to illustrate how the delays will appear when we synthesize a circuit. To keep matters simple, I have just modeled an OR gate in Verilog and synthesized it targeted at an FPGA platform. I will share these codes and the test benches. If you are interested, you can go through this flow, but for the time being, we will not look at the synthesis flow. The synthesis tool is just used to synthesize the model and illustrate the effect of delays. So what you are seeing right now is the schematic of the synthesized hardware. It's a very simple OR gate, as you can see, and the test bench is already loaded. The sources window will show the original OR gate model and the test bench. Anyway, these fonts are too small. I will be sharing these codes. Okay, let us get down to the actual purpose for which we are using this flow. We have now synthesized this model, which is a simple OR gate targeted at the FPGA platform. Now, in order to illustrate the effect of timing, we will first simulate this particular netlist the OR gate using behavioral simulation. So in behavioral simulation, only the functionality will be simulated and the delays will not be appearing in the simulation waveforms. So let us see how the simulation is showing up in the Vivado simulation tool. Okay, the waveform, the wave window which you saw first belonged to a previous simulation, ignore it. So this particular wave window is the actual behavioral simulation of the OR gate. So most of the inputs are confined to the beginning of the window. Let us just zoom out a little bit. Yes, there you are. So I have just given all the combinations of the vectors. Let me just pull up the inputs so that the output is shown at the bottommost trace. So the behavior is on expected lines. As you can see, the two inputs are A and B, and whenever either or both the inputs are high, the output is also logic high. And another thing that you can notice is when the input B changes to 1 for the first time, the output also changes to 1 as expected. And there is no delay between the transition in the input and the transition in the output. So it's a behavioral simulation, and the simulator assumes a zero gate delay model. Okay. Now let us see what happens when this code is synthesized into a target platform, in this case an FPGA. So we'll again revisit the simulation box. Let us now try to perform post synthesis timing simulation. So in post synthesis timing simulation, the behavior of the hardware when it is synthesized to a generic set of gates will be shown by the simulator. Let us see how it shapes out as far as the OR gate is concerned. Of course, the synthesis process has several subphases. We will not go into all those details. First, the design is targeted to a set of generic gates, and then again it is further subjected to another process where it is translated into the FPGA, LUTs, and so forth. Anyway, let us not go into the details of how it is done, but let us see what happens when the post synthesis simulation is carried out. Okay, so let us examine the. Please remember that the same test bench is used for performing the simulation. Okay, so let us pull A and B to the top so that the output appears at the bottom of the trace. And let us look at the instant where the input B changes to 1. That happens at the time instant 20 nanoseconds. You may recall that in the behavioral simulation, the output switched to logic 1 at the same instant. It switched to logic 1 at 20 nanoseconds. Whereas in this case, the expected transition of the output Y in response to the change in the input B is shown at the time instant 25.105 nanoseconds. And I think you would have guessed the reason for this. Now, since we are simulating the synthesized netlist, the delays of the gates are also incorporated in the simulation. So now you are seeing the simulation of a gate whose propagation delay is around 5 nanoseconds. Okay, we are still not done. Let us again revisit the simulation box. Let us go to what is called post-implementation timing simulation. In post-implementation timing simulation, the place and route of the synthesized hardware is also completed. The synthesized netlist is placed and routed, which means that post-implementation timing simulation will show delays which are more than what you have observed in the post-synthesis timing simulation phase, because now the details of the interconnects are completely specified, and as a result, the delays due to the interconnects are also now more or less frozen. Therefore, you can expect the propagation delays in the post implementation timing simulation to be more than what you had observed for the post synthesis timing simulation. Okay, let us verify this. Let us perform the post implementation timing simulation on the same netlist. This is the previous waveform. Let us ignore it. Yeah, now you have the post implementation waveforms for the post implementation timing simulation. Okay, let us just shrink the, you can see a lot of reds in the beginning. That is because the output will be, converge only when the delay has elapsed. Okay, so again let us move A and B to the top. Again, the first event in B occurs at 20 nanoseconds, as we had seen earlier. Let us see when the expected response at Y is occurring. You can see that it occurs at 6.263, at a delay of 6.263 nanoseconds, which is more than the 5 nanoseconds. It was around 5.1 or so in the post synthesis phase. Now you can see that post implementation, since the details of the interconnects are now more clear, the delay, the propagation delay has increased to 6.263 nanoseconds. So this is a small illustration of the how the delays will start emerging when we synthesize combinational circuits, right? So this is one effect of the propagation delay that we are seeing now. That is, because of the propagation delay, the expected output response to an input transition will occur only after some delay. And this is the root cause of the limitations in operational speed of various circuits. We are all accustomed to hearing about how fast a mobile phone or how fast a computer operates in terms of the clock frequencies. The root cause of all these limitations is the propagation delay, as we have seen now. And the other effect of delays are the glitches, which we will take up in the next video.